Hey everybody. So we're going to continue talking about our vector functions and space curves. So what I want to do in this video, right, so I'm starting with a vector function r of t and reminding you of something we talked about in a previous video called the unit tangent, that we give the name or the symbol typically capital T of t, and it's the you start with the tangent vector r prime and you divide by the magnitude of r prime to make it unit length. So we get this unit tangent vector. So I want to define a couple of other unit vectors that are important for our space curve. We'll do an example for finding them, and then we'll take a look at some pictures of them and some little animations to give us a little bit of a sense of what they might do for us. So I'm going to start with something we call the unit normal, okay? So the definition of this is, and we call it n of t, and we take the derivative of the unit tangent vector and divide it by the magnitude of that derivative. Again, making sure that it's a unit vector. Right? So just because the tangent is a unit vector doesn't mean its derivative is. That's why we have to have this divide by the magnitude here. And then we have one more that we will call the binormal vector. And we often call that b of t. And this is going to be the cross product of t and n, okay? So, right, these are straightforward formulas. They take a little bit of work, but they're doable. But let's say a little bit about what these are first. We already have an idea of what the tangent vector is. One thing we want to notice here, or that I'll point out, is that the vector n has to be perpendicular to t by this definition. And I'll show you why that is in just a moment. And then obviously, because it's the cross product of these two, b is perpendicular to both of them. So what we have is these three vectors are going to be perpendicular with each other. They're all going to be orthogonal, okay? And they're all unit lengths, right? If you recall that these are, since t and n are unit length, that's going to imply that this binormal vector is also unit length. So we have these three unit vectors orthogonal to each other. And that might remind you of something like the standard basis vectors that are three unit vectors orthogonal to each other. Only this set of orthogonal unit vectors are traveling around, right? They are they're at points on our space curve, right? And they're going to change directions as they move. So we'll get deeper into that in a moment. Let me show you why n is necessarily orthogonal to t. And the reason is because we know the magnitude of t, the unit tangent vector, is of course always 1, okay? And this showed up in an earlier video, but we didn't spend a lot of time on it, so I want to recall something. In general, what we can say is that if we have a vector function whose magnitude is constant, then it is always the case that its derivative is perpendicular or orthogonal to the original function. Okay, and so we're gonna prove this in a moment, or right now. So let's start this way. Notice if I take the vector r, and I'm going to drop the of t notation just to simplify this a little bit. So if I take the vector, the function r, and dot it with itself, we know that this is the magnitude squared. But since the magnitude here is c, oh, and I guess I should say c is some positive constant. So in other words, it's not 0. Well, this is trivial if r is the 0 vector. So we have the magnitude squared, in other words, c squared. So r dotted with itself has to be c squared. So now what we're going to do is take the derivative of both sides of this equation. Okay. And if you remember, there is a product rule for dot products and derivatives. We get r prime dotted with r plus r dotted with r prime on the left. And on the right, because that is a constant, the derivative of a constant is 0. Oops, sorry. Tool. That's r prime. And this is all equal to 0. Okay. Now, remember the dot product commutes, so these two terms are the same. In other words, 2 times r dot r prime is equal to 0, which means r dotted with r prime is equal to 0, which of course we know means, since we're assuming r is not the 0 vector, this only happens when r is perpendicular to r prime, right? So anytime you have a vector function whose magnitude is constant, some positive constant, non-zero constant, its tangent vectors, r prime, will always be perpendicular, right? And the intuition, I think, is pretty straightforward. What does it mean? Let's do it in 2 dimensions. It'll be a little trickier to think about in 3 dimensions, but it still works out. In 2 dimensions, for instance, what does it mean to have a constant magnitude? It means whatever space curve we're describing, whatever curve we're describing, has to lie on some circle with radius c, right? So it doesn't mean the path is necessarily a circle. The path, right, so I'll draw in red, we might just have a portion of a circle. But in any event, if we draw the tangents to this curve, right, r, remember, is going to be a vector pointing from the origin to a point on the curve. The tangent is going to be tangent to that circle. That radius, which is what r lies along, is going to be perpendicular to that tangent, right? And so that's really what this is saying. In 3 dimensions, it means it lies, oops, that got messy. I'm not going to try to draw it all, but it lies on a sphere, our path. So if this is the origin, we have some sphere, right? That's equivalent to saying its magnitude is constant. So our path might be some strange curve along this sphere, say. Well, the same thing applies. It might be a little bit harder to see, but if you can imagine drawing r, it's going to go from the origin and point at some point on this path. And tangent vectors are going to be coming off the sphere at a tangent. It's hard to draw here, but I'm hoping that you can kind of see the idea I'm going for here, right? So if you imagine the curve coming, say, right at us, the tangent vector would be right here, and the radius that r lies along is right there, and those are going to be perpendicular, okay? So there's algebraically, this is our intuition around it, okay? Well, what this means, let's just pull it back to why I was talking about that. The tangent vector, the unit tangent vector, is a vector function whose magnitude is constant. Its magnitude is 1. So its derivative, its vector derivative, t prime, has to be perpendicular to it, orthogonal to it. And all we've done to create the normal vector is make it a unit vector, right? But we haven't changed the direction. So we know that n is perpendicular to t prime by what we just showed down here. And then all we've done up here is scale it to change the magnitude. That doesn't change the fact that it's orthogonal. So we know that those two are orthogonal. And then we get that b is orthogonal to both of them because we create it to be orthogonal by taking it as the cross product of the two of them. Okay, so now with all of this in mind, let's do this for a function, and then we will look at, let's find these 3 vectors for a particular function, and then we'll look at some pictures. So I'm going to do it for a function we have seen many times already. It's a nice function, sine of t, cosine of t, and t. Okay. So I just want to compute all 3 of these vectors. I'm going to start by computing t, which means I need to first compute my derivative function, cosine of t, negative sine t, 1. I'm going to want the magnitude of this, right? And I've done this in several videos. We're taking the square root of cosine squared plus sine squared, which is 1, plus 1 squared, which is 1. So we get the square root of 2, which means the unit tangent vector looks like 1 over root 2 cosine t negative sine t 1. Okay, so that's our unit tangent vector, right? You can distribute the one, well, distribute's kind of the wrong word, but this is multiplied to each of those 3 components. So what do we need next? We want to compute n, so I need the derivative of t. So let me just box the ones I'm going for here. So here's t. To compute n, we want t prime. And this is going to look like 1 over root 2, negative sine t, negative cosine t, 0. The magnitude of t, well, if you look closely, if you ignore the constant in front, the vector negative sine t, negative cosine t, 0 has magnitude 1. Its magnitude would be sine squared plus cosine squared is 1, and take the square root, we get 1. But then we're scaling it by this, so this is in fact the magnitude of it, 1 over root 2, which means n of t, which is t prime divided by the magnitude of t prime. All that's happening is we're dividing by the constant out front, so it disappears. And so our normal vector looks like negative sine t, negative cosine of t, 0. So there's our normal vector. Okay. And then finally, the binormal vector, which is just the magnitude, the cross product between t cross n, right? That's our definition up here. If we do t cross n, we get, let's see, we will have, first of all, I'm just remembering our properties of cross products. We've got vector t crossed with vector n, and there's this scalar in front of our vector. That can just be moved to the front. That was one of the properties. So now I can ignore that and leave it out front here and then see what we get. We've got cosine of t times 0. Negative sine of t times 0 is 0, minus negative cosine t gives me cosine of t. And let's see, then we'll have negative 1 minus 0. Negative sine t minus 0 gives me negative sine t. And then I will have minus cosine squared minus sine squared, so minus 1. So I just took the cross product of these 2 vectors. We've seen those before, so if you miss some of the computation, I'll let you work that out on your own. And so here are our 3 new vectors: the tangent, the normal, and the binormal. Okay. And if we do a quick check, it's easy enough to see, take the dot products, for instance, t dotted with n, right? What happens when we dot these? I'll get, again, the scalar can stay out front until the end. We'll have cosine times negative sine gives me negative sine cosine, plus negative sine times cosine gives me positive sine of t times cosine t. So we've got a negative and a positive, the same thing, they cancel out, plus 1 times 0 gives me 0. Right? And you can do the same check for all of these. Their dot products are all going to be 0 because they're orthogonal to each other. It's also pretty quick to see that their magnitudes are all 1. Okay, so these are our tangent, unit normal, and binormal vectors for the function r of t is equal to sine t, cosine t, and t. So let's take a look at what these things are showing us. So we'll go to Geogebra. Here is our space curve. So let me just put in the axes for a moment. I don't want to leave them in, but this is this familiar helix, right? The x and y coordinates are tracing out a circle, but it's spread out over the z-axis as they spin around, as they revolve around the circle. The z-coordinate is ever growing, so we get this nice spiraling effect. Okay, let's get rid of the axes, as we're going to add lots of things to this image. So you can see pretty small, but there's a small, yeah, there it's off the line. There's a small little point that I'm imagining traveling along this particle. That's not our most important thing. Let's start adding in those vectors. So first of all, here's t. Maybe I'll zoom in just a little bit. We don't need to see so much of the curve. Here's t, the tangent vector, pointing in the direction of the tangent line, or if you imagine a particle traveling along as t grows, as t gets larger and larger, that vector is pointing in the direction of motion, right? If we looked from above, so here's starting with t at -15, our particle is traveling, I must be looking from below, I guess, because we're traveling in the wrong direction for the, oh no, okay, I did a different parameterization. In any event, there's our path around the circle, and we see that vector pointing in the direction of motion, right? Okay, so there's that vector. Now, let's add in, whoops. Let's add in the normal vector. So I've got the normal right here. So now we've got this vector n. Again, looking down the circle, notice it's perpendicular to t. It's pointing towards the center, right? So they're perpendicular to each other. And when we look at it out here in this view, it's right, they're both twisting around together in a way that they maintain that orthogonality. They maintain the fact that they're orthogonal the whole time, right? So it's a little hard to see, I know, but we get a little bit of a sense of it. And then finally, we can add b, right? Our binormal vector perpendicular to both of them. So we see, right, this little coordinate plane or coordinate, it's like we have our origin at the point A and it's moving along with the curve, right? So you can see all three of these perpendicular to each other. Let's look, let's see, let me zoom out a little bit, right? So when we're looking down the circle, we can't really see B because it's pointing into the page, right, into the screen. But when we look at it in this direction, well, right now it's off what the computer's running. There we go, a nice image of these curves. Okay, so why do we care about these curves? Well, here, let me do one more thing before I answer that question, which I won't be able to totally answer, but we'll get some ideas. I just want to show a plane. I think it's this one. So let me move this. There's a plane right now that contains the tangent and the normal vector, and the binormal vector is a normal vector to this plane. Okay, so this is the plane that contains t and n, and it moves around with them as it goes. This is the plane that comes closest to containing the curve at whatever point we've moved to, right? As we move along our curve, it's the plane that most best contains the curve at that point. Okay, so there's an interesting thing that happens about this plane called the osculating plane. It is where all the acceleration of this particle is happening. Okay, if this is a particle moving along. So let me try to say a little more about that. So let's zoom in. All right, this looks like a decent spot. Okay, so here is our curve. We're zoomed in. You can see that the B vector is supposed to be coming out towards us. Okay, and right about here, that osculating plane, the plane that contains T and N, right? You can imagine right now, more or less, I don't know if I've hit exactly the right spot, T and N live in the screen, right? That's the orientation of the plane that contains them. And one thing we can say about the curve at this point, if we can imagine in that plane drawing a circle, so I'll try to draw a circle, and the circle that we draw, right, so that's a terrible circle, but pretend that's a circle. There's a particular circle that we can draw that we call the osculating circle. This is a circle that would have the exact same unit tangent at this point, and its curvature would be exactly the same as the curvature of our curve at that point. They would share curvature. The curvature would be 1 over the radius of this circle, right? Or this circle would be 1 over the curvature of the line here. And this would also be the circle that would have the same unit normal, right? So it's sort of like saying at this point along the curve, it's like you're traveling through this circle, right? So sort of similar to how in Calc 1, when we figure out tangent lines, it's like the line that best approximates our function at a point. We can approximate our curves at a point with circles, right? At each point, it most resembles one certain circle that has the same curvature, tangent, and normal. Okay, so that's one little idea. Another little idea, I'm gonna draw this myself. If I have a curve, right, and we see its tangent in this direction. Let's talk about acceleration for just a second. We're going to get deeper into this in a later video, but this is a good moment to bring it up. One of the reasons we might be interested in these two, or in these three vectors, in particular t and n for what I'm going to do next. Well, if there's a vector, if there's a particle moving, right, it has a certain velocity. And there's two ways you can change velocities. In other words, there's two kinds of acceleration that we can think of. You can change the speed, right? You can slow down or speed up, and you can change direction, okay? Well, that acceleration we can break apart. If this thing is accelerating, we can break it apart into two pieces. One piece, right, if it's speeding up or slowing down, I'm gonna do speeding up just to simplify the drawing, we can think of as a vector, that acceleration, pointing in the direction of the tangent vector, the unit tangent, right? That's how that would describe speeding up or slowing down if it was pointing the opposite direction, but still parallel. But it's going to be in the direction of the tangent. Look at this curve, and look at the curve of this graph we did over here. Look where the normal vector is pointing. It's pointing inside the curve, right? It's the direction that the curve starts to move in. That's the other piece of acceleration. The part that's not changing the speed, it's changing the direction, right? If you look at this curve I've drawn, it's starting out moving parallel to the red line. A little while later, it's going to be moving in a different direction. So it's changing in that direction, parallel to the normal vector. And our acceleration can always be broken apart into two pieces. One parallel to the tangent vector, and another one parallel to the normal vector, right? And that is a really useful tool, right? Because you can also probably understand to some degree that that's nice to separate those two things, right? They're doing something very different. One's very much related to speed, and one's very much related to, one is related to speed and one's related to direction. And so we might want to deal with them in a different way. So physicists will often use these kinds of vectors, the tangent, unit normal, to divide up the acceleration that a particle experiences. So we'll do some work on that in a later video, but I wanted to give a little clue as to why we're caring about these three vectors. They also do something else, which is give us a moving coordinate system, right? Remember, we think of I, j, and k, our standard basis, as these building blocks for all the vectors that we have. We can make them as sums of these vectors. We could also, if this is the planet you're on and it's traveling through space in this strange path, you kind of think of yourself as the center of the universe, and all coordinate systems are determined by your orientation. Well, these would be kind of a traveling standard basis, these 3 unit vectors that stay with you and are always oriented so that, you know, forward is one of them, and then these other 2 directions that you need. And so if you're doing something like plotting trajectories and you need to understand how things feel from the point of view of the thing traveling, these are a great set of vectors to describe those kinds of motions. Okay, okay, that's all I want to say about that. Thanks, everybody. I will see you next time.